Hello everybody, welcome to part 2 of chapter 4.4. We're still talking about the fundamental theorem of calculus, but what we're covering right now is actually the second fundamental theorem of calculus, which I'll introduce you to, and we're also going to talk about net change. So, to begin, let's talk about what the second fundamental theorem of calculus says. So, second fundamental theorem of calculus. And we can just go ahead and define it. If fancy f is continuous on an open interval I containing A, then, comma, for every x in the interval, we can say the following thing. We can say that the derivative of an integral from a to x of some function of a different variable than x, so for example t, is equal to that function evaluated at x. And so, for example, let's look at something kind of simple. Let's say we were asked to evaluate the derivative d dx of the integral from 0 to x of radical t squared plus 1 dt. Notice dt is not underneath the radical. I want you to understand that, first of all, f of t is equal to t squared plus 1, that radical t squared plus 1. So that means, then, that f of x, our function evaluated at x, is the exact same everything, except it's x squared plus 1 instead of t squared plus 1. And so, in short, what we can say then is that the d dx of the integral from 0 to x of radical t squared plus 1 dt is radical x squared plus 1. That was kind of a simple example. Let's talk about something that might involve a little bit more work. So let's look at the question. Find the derivative of big F of x equal to the integral from pi over 2 to x cubed, that's going to be important, x cubed, of cotangent of t, dt. Oh, excuse me. And so, what we can do here first is recognize something. The derivative of really means that it's asking for the dx of that integral, pi over 2 to x cubed of cosine t dt. Now I want you to notice some differences between this example and the last. We aren't just given an x, like our theorem states and like the last example did. We have an x cubed. However, what we can first do is recall how we normally handle an exponent when we're simplifying things. And that's typically with the chain rule. And that's exactly what we're going to use here. So, in order to do that derivative of big f of x, right, in order to do this whole thing, the d dx of radical pi over 2 to x cubed of cosine t dt, I want you to think about it as f prime of x, big F prime of x. And I can find that by sort of doing the chain rule. And here's what I mean by that. I can do the derivative of big F of x, so I can say d big F dx times the derivative of whatever's inside, right, times the derivative of whatever I'm going to call u dx. And here's what we're going to call u. We're going to call the u piece the x cubed because we don't have a way to handle that cubed otherwise. We have to use the chain rule. So here's what we're going to do. df dx looks like what we're kind of used to normally, except, oh, I made a mistake earlier here. Make sure this is df over du. That's important because that's what's kind of helping us integrate with the chain rule here. It isn't dx, it's du because we're kind of leaving that u there until the very end. We're kind of calling that our inside function until the very end. And here's how we handle that. So df du is going to be d du of the f piece of that integral from pi over 2 to x cubed of cosine t dt. And I still have du dx over here. And now let's reiterate what we're going to call the u in here. We're going to call the u the x cubed because that's what we don't know how to handle from our theorem. That's what we have to apply the chain rule to. So we're going to say d du, and we're going to call this thing pi over 2 to u. I'm going to highlight that in different colors so you see what we're changing here. We're not calling it x cubed anymore. We're calling it to the u. And we still have cosine t dt. And we still have times du dx. And again, remember, u is that x cubed. And now, since we've replaced the x cubed with a single variable up here, we can apply the second fundamental theorem of calculus. The second fundamental theorem of calculus says that if we have a function inside to another variable, what we can say then is just that function to that other variable. So this whole thing is just going to be cosine, not to t, but to u. So we're going to simplify this whole piece as cosine of u. And then over here, we're doing du dx, or the derivative of u. The derivative of u is just going to use the power rule of differentiation, which would make this 3x squared. That's the derivative of x cubed. Now, let's not forget about u. We have to replace that u with what it was supposed to be, which was x cubed. So we're going to say cosine x cubed times 3x squared. And that is our final answer. All right. Moving on from there. Let me find my note page here. There we go. Okay. Let's talk about net change theorem. Net change theorem. So, it says that if fancy f is continuous on the closed interval from a to b, and big F is an antiderivative of fancy f on the interval a to b, then we can say there we go, that the integral from a to b of f of x dx equals big F of b minus big F of a, that can be rewritten as integral from a to b of big F prime of x dx. And it equals the same thing, big F of b minus big F of a. All we did was kind of replace the two things in here. And this makes sense because f of x is just big F prime, right? Big F prime just is the derivative of that and vice versa. So what we can say then, though, is we can go through an example with these pieces of information. Okay, I did just write down this problem, so you can pause the video to write it all down if you'd like, but I'm just going to kind of read through it right now. Chemical flows into a storage tank at a rate of 180 plus 3t liters per minute, where t is the time of minutes, and the interval is 0 to 60 is the amount of minutes, the interval of minutes we're dealing with. So find the amount of the chemical that flows into the tank during the first 20 minutes. Okay. So what we're going to do here is we're going to use that net change theorem using what they gave us. And I want to point out some things. First of all, at a rate of, we know by now that when we're talking about rates, we're typically talking about derivatives. Derivatives mean slope typically, right, rate of change. So if we're given a rate of something, that typically means that this is going to be a derivative. So what we're actually given here is that some function of t, right? We could say like this is like c prime of t, as in this is the derivative of that function. And what we also know is that we have that net change theorem, which says we can set up an integral using a derivative. So we can say of 180 plus 3t, and we're integrating with respect to t. And they also gave us an interval over which we should integrate, and they said the first 20 minutes. So that means I'm interested from when t is 0. Oh, let me use the right color. From when t is 0 to when t is 20. And I can go from here and I can just integrate this. And what I'm going to find is, first of all, that the antiderivative is 180t, and then I have 3t squared over 2. I guess I wrote that kind of silly. Maybe we should make that 3 up there next to the t squared. There we go. 3t squared over 2. And again, I'm interested from going to 0 to 20. So, oh, there we go. Now you can see that. My bad. That's a little bit better. There we go. And what I can say from there is that obviously the 0 piece is going to make this whole thing 0. So let's just talk about the 20. I would have 180 times 20 plus 3 times 20 squared over 2. And that's just going to become 3,600 plus 600, which is going to get me 4,200. And remember, in the context of the problem, we were talking about liters. So I should say then that during the first 20 minutes, the tank had 4,200 liters. Let's go on to one last example, and then I'll leave you alone. Okay, and our last example is going to talk about particle motion. And particle motion just seems to be a topic that really AP Calculus loves to revisit, so it's good that we're practicing these types of problems. And before we start in, I really want to emphasize something. I want you to know that net change in position is the same as saying displacement. And I want you to notice one other thing, that the word net in and of itself means like positives and minuses together. Pluses and minuses together, right? All the good and all the bad. That's what net means. think about a paycheck, right? Your net pay is everything after taxes, right? Not only what you work for hourly, but also when you have to subtract all the taxes. And that's really what net means here. It means everything positive and everything negative all together considered in one value. So let's go into the example. It says the velocity in feet per second of a particle moving along a line is v of t equal to t cubed minus 10t squared plus 29t minus 20, where t is the time in seconds. Where t is the time in seconds. Okay. And what we first want to answer in this question is, we will label this part A. What is the displacement of the particle on the interval from 1 to 5. Okay, so first things first, I want us to understand that that displacement is really going to be talking about the net change. So to do the displacement, we also need to understand that v of t is in relation to a position function, the derivative of a position function, right? That's s prime of t. And so what we can do here is we can use the fundamental theorem of calculus to talk about the position, right? We know if we took the integral of this, we'd be talking about its position, right? If we went kind of backwards with the velocity, we'd be arriving and talking about the position of the thing. And so what we can do then is integrate from 1 to 5, and that takes care of our interval, right? From t from 1 to 5, we're integrating from 1 to 5 of v of t dt in respect to time. And again, we're doing that over the whole interval because we're interested right now in displacement. Displacement is net change. That means all the positives, all the negatives together, the good, the bad, the ugly. Well, we want to see what all of that area is added up together. And so I can continue to write this out as 1 to 5 of the whole function, so of t cubed minus 10t squared plus 29t minus 20 with respect to t. And I can take the antiderivative of all of these lovely pieces, and I get t to the 4th over 4 minus 10 outside t cubed over 3, plus 29 t squared over 2, and then minus 20t lastly. And again, that's on the interval from 1 to 5, so I'm interested in evaluating my antiderivative. First at 5, and then minus the evaluation at 1. So, what we can write out in short, I'm just going to kind of quickly write out what all this would be, and then I'm going to show you what it is once you put it in your calculator, because we all know that's a little bit easier to look at. If we were to throw the 5 into all this first, we'd get 5 to the 4th over 4 minus 10 times 5 to the 3rd over 3 plus 29 times 5 squared over 2 minus 20 times 5. And that would be minus, if I did a 1 to the 4th, that would just be 1/4. Minus 10 times 1 would just get me 10. And over here, 29, again, times 1. That part's kind of simple, over 2, and then minus 20. So that's what everything is once I kind of write it all out. But again, it's easier just to kind of throw that in your calculator. And once you do, you should get the basic, easier to read set of fractions. 25 over 12 minus a negative 103 over 12, which simplifies out to be 128 over 12, and we can simplify that to be 32 over 3. And so, in short, we can say one more thing, that a positive answer in this case, a positive position, means that we moved to the right along that line. So when we report our answer, we say that. We say that it moved 32 over 3 in terms of feet to the right. Okay. Now let's answer one more question about this example. Let's also answer, what is the total distance traveled? And I want you to understand the difference between those two questions. For example, if you take one step forward and then one step back, you didn't technically go anywhere, right? Your total distance traveled was 0. Your displacement in that situation, though, would be 2 steps, right? Because that was the good, the bad, the ugly. 2 steps is 2 steps. That's your displacement. However, distance traveled is only going to be the positive result. So it's only going to be considering the total positive distance traveled. And here's how we can find that. It's going to be useful to give yourself a picture of this, to kind of give yourself a graph. So, if I were to graph that V of t, here's what it would look like. Get a coordinate plane going, and I'm going to be going from 1 to 5, because that's the interval I'm interested in. 1, 2, 3, 4, 5. And I'm interested in going up by 2s, 2, 4, 6, 8, and down by 2s as well. Okay. So, again, what we are doing here is graphing V of t, and here's what that looks like. We start at 1, and then we have a sort of maximum happening at about 6, while we're over 2. And then we have an x-intercept at 4, and another x-intercept at 5. And that's kind of what our graph is doing. And so it's important for us to understand that the integral, right, the integral is going to be positive in this area here. But then, to get the total distance traveled, I'm going to have to subtract the area that's negative, this little orange area right here, this little piece. And I can do that by integrating at different intervals. I'm still going to integrate the V of t function, but I'm going to integrate from here to here, and then I'm going to subtract the integration from here to here. And again, those intervals are from 1 to 4 and from 4 to 5. So here's how I would set that up. The integral from 1 to 4, which I know is going to be this big, nice, positive piece here, of V of t with respect to t. And then I'm going to subtract the integral from 4 to 5 V of t with respect to t. And I can start to fill everything in here that I need to simplify out. So the integral from 1 to 4 of, again, t cubed minus 10t squared plus 29t minus 20 dt minus, from 4 to 5, the same thing, t cubed minus 10t squared plus 29t minus 20. Okay. And so I can start to write out my antiderivatives, and those are going to be kind of the same thing, which is, again, nice. T to the 4th over 4 minus 10t to the 3rd over 3 plus 29t squared over 2 minus 20t, and that's from 1 to 4. Subtracting the exact same antiderivative, t to the 4th over 4 minus 10t to the 3rd over 3 plus 29t squared over 2 minus 20t, but this interval is going to be from 4 to 5. Okay. And so what I fill out here is a lot of stuff, a lot of algebra, but we can do it, just kind of piece by piece here. To do the 4 to the 4th, alright, so the 4 to the 4th is going to be 256. I'm going to write this out in a different color because I'll write it all out, but then I'll just simplify with the calculator so it's a little bit easier on us. 256 over 4, and then I would get 64 if I cubed 4, and then if I did 64 times 10, I get 640 over 3, plus 29 times 16, right? 4 squared is 16. 29 times 16 is going to get me 464 over 2. And then lastly, negative 20 times 4 is going to be negative 80. That's the first piece. And then I say minus everything with the 1. So 1 over 4 minus 10 times 1 over 3, 10 over 3, plus 21 times 1 over 2, and then minus 20 times 1, just minus 20. And I say minus everything in here when I substitute a 5 is going to look like 625 over 4 minus 125, right? 5 cubed is 125. 125 times 10 is 1,250 over 3. And then I have plus 25 times 29 gets me 725 over 2. And then lastly, 5 times negative 20 is going to be negative 100. And I'm kind of running out of room here, but we did already evaluate all this stuff at 4. I'm going to write it kind of below here, though. It's just this stuff over here. Minus the 256 over 4 minus 640 over 3 plus 464 over 2 minus 80. Okay. And once you take the time to put that very carefully and double check with all your parentheses and brackets into the calculator, you should get a much simpler, easier to work with 45 over 4 minus a negative 7 over 12, which turns out to be 71 over 6, and our answer is in terms of feet. And that is all I have to show you, and we'll see you in class tomorrow.